Make sure I start recording. Here we go. Okay, so today we're going through our last section on logic, inductive reasoning, and I want to just remind you of where we started in 2.1 when we started talking about reasoning. If you recall, we defined what reasoning and arguments are, okay, premises and conclusion, and then we looked at types of reasoning, and we said, okay, we've got this deductive reasoning, and we've spent a lot of time with deductive reasoning, but we talked about this inductive reasoning thing, okay? And it was, I think, important to know the difference between these types of reasonings. And deductive reasoning is easier to study, so we spent more time on it, okay? But inductive reasoning is also something that we very commonly run into. For example, anytime people are doing science, right, that's typically inductive reasoning, where you're looking at data, right, specific examples, and from that you're trying to draw some sort of general conclusion, right, some sort of scientific principle. Okay, so what we're going to be doing in this section is looking at inductive reasoning. Okay, and the basics for inductive reasoning are identifying patterns. Okay, and you can expand on that a lot and get very you can have a very detailed process. But even the process of doing science is really looking for patterns, right? You look for patterns in nature, right? Every time I drop an apple, it falls to the ground. That's a pattern. And so from that, I start to draw conclusions about gravity, okay? And we get more and more data so that we can refine our conclusions and make predictions. And that's, we start getting into the scientific method, okay? This is also going to be the type of reasoning that we're going to look at in our next unit in statistics, okay, when we want to draw conclusions, and it's very related, where we say, okay, here's some data, and from that I want to be able to draw a conclusion or say something, okay, and that's inductive reasoning. Okay, so let's look at the beginning of this process, where what we're trying to do is look at something and see if we can notice a pattern. Okay, so in inductive reasoning, because our premises start with specific observations and our conclusion is a general rule, okay, that we derive from those observations, okay, what we need to be able to do is look at our data, right, however it's given, and typically we want to find a pattern, okay? And this is why we call it going from specific to general, because we're looking at specific observations and we're looking at some sort of general rule. Okay, so in deductive reasoning, okay, what we were doing in the last few sections, what we needed to do was apply a rule that we already have. In inductive reasoning, we need to find a rule. Okay, so here's an example. Here we have a pattern, right? So circle, square, circle, square, circle, square, circle, square. Okay, and then we guess at what the next shape should be, right? Okay, and we look at this and say, I think the next shape should be a circle. Okay, because the pattern is just circle, square repeated. Okay, so the pattern repeats. Right, maybe I'll sort of underline circle, square, and it keeps repeating. All right, in this example, though, the next shape doesn't have to be a circle, right? If you were just drawing on your page and you decided to end your drawing with 2 squares in a row, that's fine. Or maybe you wanted to draw a smiley face or a hexagon or a boat, okay? You could have drawn anything, okay, and not showed me the last thing and it said, can you guess what it is? Okay, but based on what I've already seen, I expect it to be a circle. Okay, because we expect patterns to continue. Okay, and that's inductive reasoning. So that's why when we talked about reasoning back in the first section, we said that our conclusions for inductive reasoning are probably true, but they're not certainly true, okay? Because somebody could have given me a really tricky pattern where they showed me the same thing over and over again, and then the thing they didn't show me doesn't follow the pattern, okay? And if you try to trick me, then you probably will succeed, okay? But when we're looking at things where somebody's not deliberately trying to trick you, usually patterns, if we notice them, they continue. And so, we're usually going to be right. All right, so let's look at this next example. So here I see a circle, and then I see 2 squares, and then I see 3 circles, and then I see 4 squares, and then I see 4 circles, and then a blank, right? So if I sort of list this out, this pattern has 1 circle, 2 squares, 3 circles, then 4 squares. Okay. And so when I look at this, I expect my next thing to be 5 circles. Okay. Since we see 4 circles, then we think the next shape should be another circle, right? A 5th circle. Okay. In this example, the pattern doesn't exactly repeat, but we do expect the counting pattern to continue. Okay, so sometimes patterns repeat, like the circle square. Sometimes patterns continue, okay, like it's alternating between circle and square, and also increasing in number each time. Okay, so let's look at some number patterns. Other than a pattern that repeats, when we're looking at number patterns, this is an example of a pretty simple one, right? So I want you to look at the numbers in this pattern, 4, 7, 10, 13, okay? And I want you to see if you can guess at the rule and then tell me what the next 2 numbers are. So maybe you can just type them in the chat. $16, $19, good. So let's look at how you might get that. When I look at a pattern of numbers, okay, sometimes what we can do is we can say, all right, let's look and see how do we get one number from the next, and let's look at what our math operations are. Our simplest math operation is adding, so let's just see how much I have to add to 4 to get 7, right? We have to add 3, and then to go from 7 to 10, we have to add 3, and then from 10 to 13, we have to add 3. So what we do is we say, well, if I expect that pattern of adding 3 to continue, okay, then that's how we'll get a 16 and a 19. Okay. So the way that we can figure that out, to figure out how much is added, we can subtract. And this is a very simple pattern. So you could just look at 4 and look at 7 and say, okay, I know it's adding 3. But if the numbers were messier or bigger, okay, or there was a bigger difference between them, then that's how you do it. You'd say, okay, I'm going to subtract. I'm going to take 7 minus 4, and I get 3. Okay, then I look at the next pair, right? 10 minus 7 gives me 3. 13 minus 10 gives me 3. So we see at each step, we add 3, okay, to get the next numbers in the sequence. So if I continue the pattern, I take 13 plus 3 to get 16, and then 16 plus 3 to get 19. Okay. Now, what I'm doing here is taking this process that maybe look very simple, and I'm just explaining all of the little steps. Because if you're looking at something and you're having trouble finding a pattern, then you want to say, is there a process that I can try? Okay, so this gives you a process to that. Okay, this is called an arithmetic sequence because at each step we add the same number. Okay, So this next example is going to be a little bit more challenging. Okay. So let's see if we can find the number. So let's first check to see what number is added to each. So to go from 64 to 96, if I subtract these, 96 minus 64, I get 32. Okay. Now let's see for the next pair, right? For the second pair, 144 minus 96 gives me 48. Okay, well that's not the same, but let's just keep going. For the last pair that we have available, 216 minus 144 gives me 72. Okay, these aren't the same number that I'm adding each time, so that's not really a clear pattern. So maybe adding each time isn't what we're doing. So let's see if there's a common thing that we're multiplying by each time. Okay, so to figure out how much we add each time, we take the bigger number and subtract the smaller. If I want to see how much I have to multiply 64 by to get 96, okay, I can divide these to see what that missing multiplier is. So to find out, we're going to divide. Okay, so I'm going to take 96 divided by 64, and I get 1.5. Okay, I'm going to take 144 divided by 96. That also gives me 1.5. Okay, and things are looking a little more promising here. Let's try the last one. 216 divided by 144, and I get 1.5. So here I can see that each step, what we need to do is we multiply by 1.5. So to get the next two numbers in the sequence, I could take 216 and multiply by 1.5 and get 324. So then I take I'll write that down, my 324. And then I'm going to take my 324 and multiply it by 1.5. Okay, that gives me 486. So that's my sixth number, right? 486. Okay, and this is called a geometric sequence. Okay. At each step, we're multiplying by the same number. Okay, so if I look at number sequences, we had an arithmetic sequence where we add the same number each time, and then a geometric sequence where we multiply the same number each time. Okay. All right, now there are other number patterns that we can come up with that that aren't just looking at, multiplying or adding the exact same number each time. Okay, so let's look at another example. We still want to try the same process though, where we try to break it down. Okay, so let's look at how much we have to add each step. Okay, so let's look at how much we add each step. So to go from 2 to 5, I have to add 3. To go from 5 to 10, I have to add 5. To go from 10 to 17, I have to add 7. Okay, that's not adding the same number each time. So let's check and see, maybe it's a geometric sequence. So let's see what we have to multiply by each time. Okay, so to go from 2 to 5, okay, remember we divide to see how much it is. I have to multiply by 2.5. Okay. To go from 5 to 10, I have to multiply by 2. To go from 10 to 17, I have to multiply by 1.7. Okay, and that's again not the same number each time. That's not really following a clear pattern. Okay, so now let's try something else. Let's look for a pattern in the numbers that we wrote down, either in the differences or the multiples. Okay, so when I look at 2.5 to 1.7, I don't see a really good clear pattern there. But 3, 5, 7, those look like I'm just, going through the odd numbers. Okay. Or another way to look at it is if I look at these as being a pattern, right, or being a sequence of numbers, okay, is there a pattern to this sequence? Well, to go from 3 to 5, I add 2, right? To go from 5 to 7, I add 2. So maybe what we're doing is we're adding 2 to this number that we have to add each step. Okay. So I start by adding 3, and then I'm going to add 2 to the number that I have to add at each step. So I add 3 to get to 5, and then I increase, right, I add 2 to the number I'm going to add. So I'm going to add 3 plus 2 is 5. So I add 5, and 5 is 10. Okay. All right, now the number that I'm going to add each time, I add 2 to it to get 7. So 10 plus 7 is 17. Okay. So then if I keep going, the number that I have to add each time is going up by 2. So it's going to become a plus 9. And 17 plus 9 will give me 26. Okay. Then I add 2 to the number I'm going to add, right? So 9 plus 2 gives me an 11 that I'm going to add. And then 26 plus 11, let's put my 11 here, stay consistent. 26 plus 11 will give me 37. Okay. So that one was a little bit more complicated. All right. I want you to try this next example. So I'll give you a minute to work on it, but go through the same process. Look at what are the numbers that we add, what are the numbers that we multiply, and if you don't see a pattern, then see if you can find a pattern in either the things that we add or the things that we multiply. Yeah, it looks like a couple of you got it. All right, so let's go through it, and let me write it down so that we can all sort of see the same thing that we're talking about here. Okay, if I look at the numbers that I add each time, here I'm adding 0, here I'm adding 2, here I'm adding 8, here I'm adding 24. Okay, I'm not adding the same thing, so let's check the multiplying side. Here I multiply by 1. To go from 2 to 4, I multiply by 2. To go to from 4 to 12, I multiply by 3. To go from 12 to 24, from 12 to 48, I multiply by 4. Now, these aren't the same number either, but I can definitely see a clear pattern in the numbers that I'm multiplying by. The number I multiply by goes up by 1 each time. Okay, so then the next number that I multiply by will be 5. 48 times 5 gives me 240. Okay, and then the number I multiply by goes up by 1, so it's going to be a 6. And when I multiply by 6, I get 1,440. Okay, and I find it interesting that the two of you in the chat came up, wrote it down at like the exact same time. That was pretty good. Okay, so we add num1 to the number we multiply by each time. Okay, so now let's look at this next pattern. Okay, to go from 8 to 11, I have to add 3. To go from 11 to 6, I don't add, I subtract 5. To go from 6 to 9, I add 3. To go from 9 down to 4, I subtract 5. To go from 4 to 7, I have to add 3. From 7 to 2, I subtract 5. Okay, I'm not going to write down the multiples here, which aren't going to be nice whole numbers anyway. But I can already see a pattern, right? I'm alternating between adding 3 and subtracting 5. Okay, so following my, or continuing on, right? Following my pattern, if I add 3 to 2, I will get 5. And then if I subtract 5, I will get 0. So I think the next two numbers would be 5 and 0. Okay, this last one is really tricky. Okay, but I think it's fun. And when you write it out, it looks kind of neat. So go ahead and write out the, how much you have to add each time, right? The differences. Don't worry about the multiples. Look at how much you have to add each time and look for a pattern there. Or I'll even write out the differences here. So here I add 0, and I add 1, and then I add 1, then I add 2, and I add 3, and then I add 5, and I add 8. Did anyone see a pattern? So I can see that I've got 0, 1, 1, 2, 3, 5, 8. I can see that if I look at my number I have to add each time, it's just an earlier number in the sequence, right? The sequence itself tells me what I need to add next. So the numbers we add have the same pattern as the sequence itself. Okay, so maybe I can't even figure out what that pattern is, but I can just look at it, right? So if I look at this, right, I have my 1, 1, 2, 3, 5, 8. The next number that I have to add, what comes after 8 in the sequence, I can see is a plus 13. Okay, so I add 13, right? So 21 plus 13 gives me 34. And then I say, okay, after 13 in the sequence comes 21, so the next thing that I add is 21. Okay, 34 plus 21 gives me 55. Right? And I could keep going because after 21 in my sequence comes 34, so the next thing I'm going to do is add 34. Okay, so we could just keep building this up. I'm not going to write this down, but just a nice piece of trivia. This is actually a famous sequence. It's called the Fibonacci sequence. So you can look it up, and it's when you look it up, Like you'll see a bunch of spiral patterns, and you'll be like, what does that have to do with the sequence? But it might be fun to explore. But not in class today. All right. Let's look at what does induction look like in real life. When I look at patterns and numbers, that seems like a fun game, but it doesn't really seem like, useful in my everyday life. Right? There's nowhere where in my life I feel like I have to, at least outside of a math class, look at a list of numbers like this and guess at what the next number is. Okay. What we're doing there is we're just looking at really basic, pattern identification and trying to be explicit about how we do this. Okay. So let's go ahead and look at something a little bit more realistic, a situation, right? All right. So let's jump right into an example. Grace is supposed to arrive at work at 9 a.m. She has been late for work 3 times this week, and her boss is mad. She thinks about what time she left for work and what time she arrived each day this week. Okay. So here's our 5 days in the work week. So she left at 8:45, arrived at 9:10. That is not on time. She's supposed to get there at 9 o'clock, right? Okay. And we can look at her travel time, right? 25 minutes. Okay. She left at 8:25, got there at 9:40, okay? It only took her 15 minutes to get to work, and she was on time. All right, that's good. She leaves a little bit later, right, at 8:30, gets there at 8:50. That's still on time, okay? Took her 20 minutes to get to work, okay? She left at 8:40 on Thursday, right? Gets there at 9:05. That's late to work. That's no good, okay? Now notice what she's doing, right? So, she was late to work, so she leaves earlier. She's on time, but she got there 20 minutes early. So the next day she's like, all right, well, let me leave 10 minutes later. Still 10 minutes early. Okay, so let me leave 10 minutes later. But leaving 10 minutes later, now she was late because it took her longer to get to work. Oh, that's no good. Okay. And then Friday, well, maybe something happened in the morning. Okay. So what pattern does Grace notice here? All right. If we pick this apart a little bit, I noticed that the amount of time it takes to get to work, and we sort of already did the subtractions here. Okay. It takes her a different amount of time to get to work each day. Okay. All right. What else do we notice? Well, it looks like the days that we leave later, right, like the 8:45, right, it took 25 or 30 minutes. If we leave a little bit earlier at 8:40, 25 minutes, okay, still about the same. If we leave at 8:30 or 8:25, then it takes us less time. So it seems like when she leaves later, it takes longer. So maybe there's traffic building in the morning. I don't know if any of you have had this experience with commutes, but sometimes as the morning goes on, traffic gets worse and worse, so it takes you longer to get there. Okay. Now, what's the other pattern that we noticed? The longest that it took her to get to work was 30 minutes. All right, well, so if we want to be safe, if the longest it's taken to get to work is 30 minutes, okay, and it seems like, leaving later will give you a longer travel time, okay, then if we want to make sure that she's always on time for work, then she needs to leave by, 8:30 at the latest. Okay. All right. This reasoning is inductive because Grace has based a plan on the future, okay, based on specific past instances. Okay, or you could just say observations, right? When we look at what's happened in the past and we use that to make a plan for the future, that's like drawing a general rule, right? It's the same idea. So just like when we were finding, patterns in numbers, this is kind of the same idea. Notice though that when we look at things in the real world, typically they don't follow as neat a pattern, right? So like, leaving at 8:45 might take 25 minutes or it might take 30. Okay, it's not always exactly the same. And that's just what happens when we make real life observations. Usually the patterns don't fit quite as cleanly. They're not perfect. Okay, but we can still make conclusions based on them. Okay, so once we started talking about deductive reasoning, right, one of the things we jumped right into was talking about what are ways that the reasoning can go bad, what were fallacies. So what we're going to do now is look at what do fallacies look like with inductive reasoning. Okay, so here's some examples. So our first example, English teachers are all mean. I've had mean English teachers in both of my last 2 English classes. Okay, and just like we did with deductive reasoning, we'll give names to these. And this one is called a hasty generalization. So an inductive argument uses hasty generalization when it concludes that all or most members of a group have some property based on observing a small number of members. Okay, so if you've only had 2 English teachers, okay, it may not be that they're English teachers. You just may have had, 2 mean people for teachers. Okay, so that's not very many. If on the other hand, you're finished high school, right? So you had 12 years of school, and in every year your English teacher was terrible, okay, but your math teacher was always very nice. Well, then maybe that's more evidence to draw an inductive conclusion. Okay. All right. So when we have a small number of members, then we want to be careful about that. But is 12 enough? Right? 2 definitely seems like a small number, but like what would be a big number, right? So we have to think about what is a small number of members anyway. Okay. I definitely think 2 is small, but there's not a really clear-cut line as to how many is enough. Right? Okay, let's look at another example. In a TV commercial, a car insurance company lists the amounts that customers have saved by switching their car insurance as $510, $475, $490, and $535. They want you to come to the conclusion that if you switch to their car insurance, you will also save hundreds of dollars. Okay, this logical fallacy is called cherry picking because what we're doing is we are selecting the specific observations that support a desired conclusion. Okay, so if you switched to this car insurance company and your rates went up, okay, you wouldn't be in their commercial, right? So people whose rates would be higher either didn't switch their car insurance, right? Because if you're shopping around and you say, oh, your rates are going to go up, you probably won't make the switch. And if you did, right, if you did pick up their insurance and you ended up paying more, then you wouldn't make it into the commercial. Right? Commercials don't advertise when things don't work well. They advertise the best case. Okay, so that's called cherry picking. Let's look at another example. A politician notes that people who own horses are significantly less likely to be homeless than people who don't own horses. He proposes a policy to give away free horses to reduce homelessness. Okay, and it's not that this is something that I've ever heard. Okay, But this is a good example of like, a type of reaction that people can have. Okay, so this inductive argument is called faulty causation because the conclusion states that one factor causes another without any additional evidence. So it's probably not that owning horses makes you less likely to be homeless. Okay. What's happening is that both horses and homes are expensive. Okay. And someone who can't afford a home also can't afford a horse. Okay. So that's probably why homeless people don't have horses. Okay. So it's not owning a horse that's keeping you in your home. It's having a lot of money in the first place. Okay, so that's an example of faulty causation. Okay. So all right, let's look at these in a little bit more detail. Hasty generalization was a little bit tough because we said, well, it's the problem is you picked a small number and we didn't really say what a small number was. 2 was small, but we didn't say how big is enough. So let's look at these 3 examples. I asked my 4 teenage cousins, and they all use TikTok. Therefore, TikTok is popular with teenagers, right? So that's argument number 1. Argument number 2, I surveyed 500 teenagers, and 435 of them use TikTok. Therefore, TikTok is popular with teenagers. Same conclusion, but we asked more people. However, in this one, not everyone uses TikTok. Okay, it was all 4 of our cousins, but not everyone out of the 500 we surveyed. But 500 is a much bigger number. Okay, our last argument. I surveyed 10,000 teenagers, randomly selected from all 50 states, and 8,928 of them use TikTok. Therefore, I conclude TikTok is popular with teenagers. Okay, these arguments all have similar premises and the exact same conclusion. Okay, but they're different arguments. Okay, so in argument number 1, we only asked 4 people, and you may not know how much is enough, but 4 is a small number. So argument number 1 is an example of hasty generalization. Okay, because 4 teenagers isn't very many. Okay, argument number 1 also might be bad because we could be cherry picking. Okay, because in this case, the 4 teenagers that we talked to were all, related to me, right? I only asked my family. Okay, and maybe people in my family, share a lot of commonalities. For example, if one of them is into TikTok, maybe they would talk about that with the others and they would all get into it and try it out. Okay, or if they decided it wasn't cool, then they would all go to something else. Okay, not necessarily, but the idea is that this isn't really giving me a good representation of all teenagers. Okay, if I look at argument number 3, it's better than argument number 2. Okay, 1 is just right out, right? It has definitely a problem with hasty generalization and probably a problem with cherry picking. But between arguments 2 and 3, I both have a lot of people, right? 500 is a big number. 10,000 is a big number. I feel confident neither one of those are going to be a hasty generalization. Okay, but argument 3 is stronger than argument 2 since there are more teenagers in argument 3. Okay, and then there's this whole bit about picking from all 50 states and randomly selecting them. Okay, so the parts about the randomly selected teenagers okay, and about picking from all 50 states, okay, are probably there to show that I wasn't cherry picking. Okay, so even if I survey 500 teenagers, again, if I pick all 500 teenagers, for example, from the same high school, okay, maybe that's a trend or a fad in that high school, but it's not a nationwide trend. Okay, so again, that wouldn't be a good way to draw a conclusion about all teenagers from just that one school. Okay, but if I'm picking from geographically all over the place, and I'm randomly picking out of those states, then this seems that I'm safeguarded myself against cherry picking, whether it was intentional or accidental. Okay, so you don't have to be intentionally, like with the Geico or whatever it is commercial. Okay, here obviously you're going to look at how much people save, and if they don't save very much, they're not in the commercial, and people who do save a lot get to be in the commercial. So that's intentionally cherry picking to make a more effective ad. Okay, here maybe we weren't cherry picking on purpose, but if we just surveyed our local high school, we may have accidentally come across a group of people that are sharing in the same fad or something like that, okay, and be guilty of cherry picking. All right, so how many teenagers do I need to ask? Okay. Can my conclusion be more specific than just TikTok is popular? How can you know I wasn't cherry picking? Okay. In a sound inductive argument, my conclusion is probably true. That's something that we talked about right at the beginning, right? In deductive reasoning, if you have a valid argument and all your premises are true, okay, that's a sound, valid deductive argument, then the conclusion is certainly true. We said that with an inductive argument, if you have a valid argument and the premises are all true, the conclusion is probably true. What does probably mean? Okay. Does that mean the same thing to you as it does to me? Can we be very specific about what probably means? Okay. So all four of these questions are questions that we're going to answer in the statistics unit. Okay. So what we're leaving off with here in logic, in order to delve in more deeply, we need to start doing statistics. And so that's going to be our next unit. Okay, so that kind of gives you a nice little segue. However, this is as far as we're going to go in this unit. So this is the end of logic. All right.